Okay, round of applause for Matt with using unsafe.Pointer to explore Linux system calls.
Cool, okay, mic good? All right. Hi everybody, my name is Matt Layher, and today I'm going to talk about using unsafe.Pointer to explore Linux system calls. So you can find me on GitHub, Twitter, mdlayher.com, pretty much everywhere else as @mdlayher, and you can find the contents of this talk as well as my others at my talks repository on GitHub. So I'd like to thank Fastly here for sending me today. Fastly is a powerful edge cloud platform, and we use a lot of Go at Fastly, so if you're interested, please come speak to me afterward, and yeah, thanks Fastly for sending me to Gocon Canada. So today we're going to talk about package unsafe. So package unsafe is a pretty interesting and unusual part of the Go standard library. It contains operations that step around the type safety of Go programs. And we're going to dig into what exactly that means and why that's useful. So as it turns out, package unsafe and Linux system calls really do go hand in hand. And sometimes you need an escape hatch from Go's type system in order to do things like interface with the operating system or CGO or etc. But there are some rules you have to read and understand to use unsafe safely. And the unsafe.Pointer documentation mentions them right there. So the Go vet tool can catch some of the mistakes you might make. However, you really need to read and understand these rules in order to use it safely. So first, before we talk about unsafe, let's explain what a system call actually is. You can kind of think of it like a function call into the Linux kernel. It's used to access resources such as files, hardware, and etc. So for example here, I have this C pseudocode, my user space code, and my kernel code. In my user space, I'm going to open a file descriptor to the dev null file. The kernel will see this, give me a file descriptor, in this case let's call it 3, and then it'll actually open handle to the dev null file itself. And then from there, I can use that file descriptor handle in other system calls to refer to that same file in the kernel. So for example, if I say write with my file descriptor in some buffer of bytes, the kernel will see this, and it's going to write the buffer of bytes B to the dev null file. So in Linux, many things are kind of like files, right? This Unix philosophy of everything is a file. And you have system calls such as open, close, read, and write that map pretty cleanly as like file operations. However, not every operation maps cleanly to these paradigms. So for example, there is ioctl, which is short for I/O control. And this is kind of the catch-all for operations that don't cleanly fit the Unix stream I/O model. So primarily, you would use an ioctl for passing data back and forth between the kernel and user space. So let's say, for example, here we want to use ioctl in C, just to give a quick example. So let's suppose we want to retrieve the VM socket's context ID for our system. What exactly that means today isn't important. Just know it's an unsigned 32-bit integer, and we're going to fetch it from the kernel using an ioctl. So we open a handle to our dev vsock file using open, and then we declare our local variable uint32t of CID, and we call ioctl, specifying the file descriptor, the command we'd like to perform, and the address of the CID local variable. Assuming this returns successfully, we now have this variable populated by the Linux kernel. But of course, this is a Go conference, so we're not going to implement this in C. How do we replicate this program in Go? So today, in order to understand unsafe system calls and how these things fit together, we're going to have to discuss some prerequisites as well. Things such as Go's type safety, the memory layout of Go types, as well as endianness, how things are actually laid out in memory. We're also going to introduce package unsafe and explain some of its use cases, and we're also going to establish some guidelines to help you make safe use of package unsafe in your own applications. So first, what exactly is type safety? Type safety provides safeguards for the programmer, preventing you from making mistakes. So for example here, let's say we're trying to print a couple of things to the screen. We have this integer 1 and this string ABC, and we're trying to add them together. Go's type system will not allow you to do this, and that's because Go is a statically typed language. So the compiler is going to check your data types of your variables and functions and etc., and enforce type safety for you. However, you could perform this operation if you wanted to by using, for example, the strconf package, taking the integer 1, converting it to a string, and then you can use the plus operator for concatenation. So if you come from like a dynamic language, it might see the first statement, 1 plus ABC, and say, okay, I know what you mean. But Go requires you to do this explicitly instead. So in order to understand unsafe as well, we need to know how Go types are actually laid out in memory. So for example, Go has many different integer types, including the int and uint types we'll talk about on the next slide, but also several fixed size integer types that occupy 8 bits per byte. So for example, int8 and uint8, 16, 32, and 64. And these occupy 1, 2, 4, and 8 bytes of memory respectively. The int and uint size are pretty special. So for example, their size actually varies by your CPU architecture. So if you're on GoArch or Gorch, I understand, equals 386, these will occupy 4 bytes. But if you're on AMD 64 instead, most computers these days, it's going to occupy 8 bytes instead. So for this reason, I actually recommend avoiding these where possible if you're writing unsafe code. They can make things a little bit more tricky and more difficult than you might need otherwise. So as it turns out, the same rules also apply for Go arrays. So if we have an array of 1, 2, 4, or 8 bytes, it occupies the exact amount of memory you might expect, and actually these have the same memory layout as, for example, those integer types we talked about before. However, arrays are not as common in Go, so what about slices? Slices are a little bit more tricky, and you need to be careful with unsafe code because you need to know if you're referring to the slice header itself or the backing array of the slice. So if you do make slice of bytes with 8 here, it's actually going to create a slice in memory that has this slice header with a length, a capacity, and then a pointer. And the pointer actually references some backing array. So this is explained on the blog, blog.golang.org, Go slices usage and internals. But the point of the talk here today is just to know that if you're working with slices, you need to know if you're actually referring to the slice header or the data inside the slice. More often than not, you want the data, but both are useful for certain situations. We also need to discuss endianness. So you can think of this as the way that a particular CPU lays out values in memory. And it's sometimes also called byte order. So for example, if you have the uint16 value 1, it can be laid out 2 different ways depending on your CPU. So in big endian, this is laid out as 0, 1 in memory. And this is also known as network byte order. So for example, most network protocols are transferring things in big endian instead of little endian or otherwise. But there's also little endian, and this is actually laid out as 1, 0. And this is the native byte order of your Intel or AMD x86 CPU. So this can be a little bit tricky, and you need to understand the differences between the two. As it turns out, you can actually use both of these in Go directly by using the encoding binary package. So say, for example, I have a uint16 value of 1, and I want to convert it to both big and little endian formats. We allocate 2 byte slices, both of length 2. We use binary big endian and binary little endian to store these in byte slices. And if we print them to the screen, we'll see that the layout is as we'd expect. 0, 1 for big endian, and 1, 0 for little endian instead. So now that we've discussed these prerequisites, we can finally dive into package unsafe. So package unsafe actually has a pretty brief API documentation, but I want to call out one sentence here that's quite important. Packages that import unsafe may be non-portable and are not protected by the Go 1 compatibility guidelines. So as soon as you bring unsafe into your application, you really are expected to know how to use it properly, safely, and in a forward-compatible way with future versions of Go. The API for unsafe is pretty brief, but there's this pretty interesting thing going on here called type arbitrary type int. And this doesn't actually exist in the real Go language. This is just used for documentation. The compiler actually implements these operations in a special way under the hood, and you can use literally any type you want with these unsafe operations. For today, we're going to talk about a couple of them in particular. So the first is the size of function. So you can use unsafe size of. So for example, with integers here on my AMD 64 machine, to figure out how much memory a value actually occupies. So say, for example, you want to find out the size of uint 8, 16, 32, 64, and finally the native uint type. For the fixed size ones, it's exactly what you'd expect. 1, 2, 4, 8 bytes respectively. However, because I'm on an AMD 64 machine, the size of uint is also 8 bytes. But if you were on a 32-bit machine instead, it would be 4. You can also use unsafe size of with structures. So for example, you would think this struct might occupy 14 bytes. It's got 3 fields, they're laid out back-to-back in memory of sizes 8, 4, and 2. So adding that together you get 14. But unsafe size of tells us we actually have 16 bytes here instead. So what's going on is this struct definition is actually being padded to the next machined word size. In this case, 64 bits on my machine. So you can think of it like there's this unexported member here that's an array of 2 bytes that pads it up to the correct size. And now we see the unsafe size of reports the same size we would expect. So now that we've discussed unsafe size of and finally set the table, let's talk about unsafe.Pointer and the interesting and dangerous things you can do with it. So you can do a lot of different operations with unsafe pointers, but I think perhaps the most useful one of these is this. And let's say, for example, that T1 and T2 are 2 different Go types. So provided that T2 is no larger than T1, and that the 2 share an equivalent memory layout, unsafe pointer conversion allows reinterpreting data of one type as data of another type. But what exactly does this mean? Let's go through an example. So let's say we want to convert a uint16 to an array of 2 bytes. We both know these occupy 2 bytes of memory, but Go's type system will not allow you to do this conversion directly. As you'll see, we get a compiler error. However, you can use an unsafe pointer conversion to actually defeat Go's type system and step around it. So what we're going to do first is we're going to check and make sure the sizes of the two types are equivalent. This is very important with unsafe code, or else you could get into some pretty funny things we'll discuss shortly as well. In this case, we know that uint16 and an array of 2 bytes both occupy 2 bytes of memory, but it's always good to do this sanity check anyway, especially when you're working with things like structures that their size may change over time, and etc. So if the size of the A is not exactly what we'd expect, we panic and crash our program. This is better than the alternative, trust me. So next, we're going to do this pretty interesting line here. There's a few different things going on. We're going to break it down, don't worry. But then when we print this to the screen, we'll see we now have an array of 2 bytes, and the bytes are 1, 0. So this is actually converting the uint16 value of 1 to 1, 0 in an array of 2 bytes, which is little endian, which is the native endianness of my CPU. So what exactly is going on? Let's break this statement down into a few different steps. So first, we're going to take the address of the variable A, and this will produce a pointer to a uint16 value. So next, you can convert that pointer to a uint16 to unsafe pointer. This is one of the interesting things you can do with the unsafe pointer type. You can convert between any Go pointer type and unsafe pointer, and also back and forth. So what we'll do next is we're going to go ahead and take that unsafe pointer and reinterpret that as a pointer to an array of 2 bytes. So that's a pretty unusual Go type by all standards. However, you can dereference that pointer, and now you have an array value. So an array of 2 bytes together as a value format. So over time, you'll get used to kind of that one-line operation, but if you wanted to, you could also write out the same operation with intermediate variables. So for example, we have A, we take the address of A, convert that to unsafe pointer, convert that to a pointer to an array of 2 bytes, and then dereference that, and the same conversion can be done in multiple lines. There's a quick note here. So slices are typically what you're working with in Go, but when you're doing unsafe pointer conversions, you're going to work with arrays instead, and not slices. So for example, if you want to take that conversion we just did and retrieve a slice out of that, you can use the slicing operator with square brackets here. So you add an extra pair of parentheses, and the square brackets and the colon, and that is the slicing operator that produces a slice from an array. Or conversely, if you want to convert the data in a slice to, for example, uint16 here, we're going to take the address of the first element of the slice. So for this, we're referring to actually the backing array of the slice and not the slice header. There are situations where it's useful to convert the slice header as well, but we're not really going to get into that today. So now that we've talked about some of the things you can do with unsafe, let's enter the danger zone and show you things you probably should not do with unsafe. So the unsafe pointer documentation covers 6 patterns which are considered valid, and you really need to read and understand these patterns before you make use of unsafe in your applications. And I was hoping I'd be the first one to use this graphic today, but I guess not, so. Oh well, thanks Ashley McNamara, appreciate it. So first, you can actually read arbitrary memory with unsafe. You have to be really careful in your use of unsafe, so for example, always checking the sizes of your types. But for example here, let's say I want to convert a uint16 that occupies 2 bytes of memory into an array of 4 bytes instead. So if I do this and I run this example on the playground 3 times, the first 2 bytes are 1, 0, so what we'd expect, but the second 2 bytes are totally arbitrary. So what we've done is we've read arbitrary memory from somewhere else in our program, so you can potentially expose things like user passwords or TLS private keys or other very sensitive data. So don't do this. This is why the size check is really important, and it really is better to crash your application than run something like this and possibly expose sensitive data to your users. As it turns out, you can also do pointer arithmetic in Go as well. So some of you may remember this from C. This is where the uint pointer type comes in, which is another one of Go's integer types, and you can convert between unsafe pointer and uint pointer, and also do pointer arithmetic. So we've got a pretty interesting example here. We've got a slice of uint32 values, and we're going to do pretty much the worst possible way to print out a slice in Go, right? So instead of using for range, we're actually going to iterate over the memory addresses instead. So we take the address of the first element in the array, and then we add I times 4 for each iteration. So instead of iterating the values, we're iterating the memory, and then converting the memory addresses all the way back to uint32 and printing it out. So I'm not saying you should do this, but you totally can, and it's pretty fun. So finally, you can also write arbitrary memory using unsafe as well. So let's say, for example, we have this value v. It lives somewhere in your Go memory, and I'm just going to go ahead and overwrite whatever data lives in this address. So I'll take the unsafe pointer of the address of v, convert that to uint pointer, do some pointer arithmetic, convert back to unsafe pointer, convert to a pointer to an array of 4 bytes, dereference that, and then overwrite whatever happens to live at that address, and On my machine, I get a seg fault. So this is probably the best case scenario here, right? So runtime fatal error fault, you get the stack trace, but I guess even worse, you can potentially overwrite some important memory, possibly causing a security problem in your application. Like, you really don't want to do this. So you have to be really careful when you're messing with these kinds of things. So now that you've seen these kind of like terrible uses of unsafe, you might be wondering, when is unsafe actually appropriate to use in my own applications? As it turns out, working with system calls often involves a lot of unsafe code. But instead of using the syscall package directly, we're going to use golang.org xsysunix, because that is essentially the modern day replacement on Linux systems. So working with system calls is pretty often going to involve some kind of unsafe operation. For example, a lot of the kernel's C APIs, you're basically passing void pointer or whatever else. An unsafe pointer is kind of the Go equivalent. So you can use this to pass arbitrary data back and forth between user space and the kernel. But Go's syscall package is deprecated these days. It's been essentially frozen since Go 1.4, so use xsys instead. And there are certain system calls that are really flexible. Things like ioctl, getSockopt, setSockopt, and these are actually too flexible to expose like a good general purpose API. So what you'll find instead in the Unix package is wrappers such as ioctl getInt, setSockopt linger, and etc. So we don't want to expose unsafe pointer directly in an API because it pretty much becomes impossible to use correctly, at least in a general way. So this is the actual definition of ioctl in xsys Unix. It takes 3 arguments, which is a file descriptor integer, a request, such as the get local context ID we talked about earlier, which is usually from like a C header or something, and also this argument uint pointer. And this is where things get really interesting, because you could pass a pointer here, so like a literal memory address, or even just a regular integer, because ioctl pretty much doesn't care. You can do kind of whatever you want depending on the driver you're talking to. And the way this is implemented is actually by calling into some pretty interesting assembly stuff in this syscall function. We're not really going to get into that. Just assume that this works. So let's revisit our example in C really quick. We're going to open a file descriptor to the dev vsoc file. We take our uint32 local variable. We're going to pass the address of that into this ioctl with the command we want. And assuming this works as we'd expect, that variable is now populated. So we can do this with Go, but in order to do it safely, we have to talk about one of the rules of unsafe. If an unsafe pointer argument must be converted to uint pointer for use as an argument, that conversion must appear in the call expression itself. And we'll explain why. So here's that same code ported to Go. So what we're going to do is we're going to call obs open of dev vsoc, and now we have an OS file type. We've copied out the definition of ioctl from xsys Unix because we're going to pass an arbitrary unsafe pointer to it. So what we do is we take the file descriptor of our file, we specify the command we want to perform, take it from the C header, and now we're going to do a couple of things at once. We take the address of the uint32, so pointer to uint32, convert that to unsafe pointer, convert that to uint pointer. And you'll notice we're doing it all within the call to ioctl itself. So there's a tricky thing going on here. Say, for example, you were to make this uint pointer conversion somewhere else in your application. So you do it, and you go somewhere else for a while. You do some database calls, some network calls, whatever else. It is possible for Go's garbage collector to move values around in memory. And if you're storing an address in the uint pointer and not using it immediately, it's possible that by the time you get back, that address might no longer be valid. So this could crash your program, or worse. So this is really important, and you need to make sure you do all these conversions directly inline in the function call in order for this pattern to be recognized properly by the compiler and to do this safely. So as it turns out, when you're passing integers back and forth between the user space and kernel boundary, this uses the native endianness of your system, which you can discover by doing something like this. So say, for example, I take our uint16 of 1 again, and I want to figure out the byte pattern here to determine the endianness of my system. We're going to do an unsafe pointer conversion to an array of 2 bytes. If it's big endian, it'll be represented as 0, 1. If it's little endian, it'll be represented as 1, 0. And if something else happened for some reason, we're just going to go ahead and panic because it's no longer safe to continue, right? So as it turns out, this property of native endianness is actually pretty useful. So this is the Linux taskstats interface. This is used to expose a bunch of statistics about a process, and it contains this pretty large type. It actually occupies 328 bytes of memory at the time of this presentation, and I actually had to split it up over 3 columns here just to fit the whole thing on the screen. So sure, you could parse bytes into fields manually using native endianness, but this could be pretty error-prone. So as it turns out, all you really need to do is a single unsafe pointer conversion to your Unix taskstats type. So let's say, for example, we have a byte slice that we fetch from something like ioctl or the kernel netlink interface. Then we're going to check the size of the taskstats structure and verify that the length of our byte slice and the size of the structure actually match completely in order to avoid, possibly reading arbitrary memory or writing arbitrary memory. Remember, these size comparisons are really important. So from here, since we're passing out a byte slice, we take the address of the first value of the byte slice, which points to the backing array. We're going to do the unsafe pointer conversion, convert that to Unix taskstats, and we're done. So now we've taken this 328 bytes of whatever and converted it to our structure directly, and we don't have to care about endianness at all. It just works. So you can do a lot of other really interesting things with unsafe. You can potentially improve your performance in certain situations. So for example, there was one time where I was doing an API that had like aligned 8-byte, trying to check a slice of bytes for all zeros. And sure, you can check 1 byte at a time, but if it's aligned on an 8-byte boundary, you can actually convert from an array of bytes to an array of uint64s, and then suddenly you're checking 8 bytes at a time for 0. So you can do some pretty cool stuff with unsafe. I just wasn't sure if I'd have time to talk about that today. You can also use it with CGO. So for example, passing data back and forth between C and Go. And also, you can actually access unexported identifiers from other packages if you import unsafe and use this Go link name directive. So the runtime uses this to great effect actually to expose certain things to things like package time, but not to general users. But yeah, you can do that if you want with unsafe. So in summary, I'm sure you're not surprised, but with great power comes great responsibility. And as soon as you import package unsafe into your applications, you are expected to know how to use it safely, properly, and in a forward compatible way. But you shouldn't fear package unsafe because it really is a vital part of what makes Go work with things like system calls, CGO, and many other applications. And when in doubt, seek guidance and ask questions. There are lots of folks out there who have done lots of really interesting things with unsafe and reflect, and actually a few of us congregate in the Dark Arts channel on the Gopher Slack. So please come join us. So I've written a blog on the topic. If you're interested, you might want to check that out on mdlayher.com. You can look at the source code for the packages I talked about today, my taskstats and vsoc packages. And finally, I'd like to thank this group of folks from the Dark Arts channel for helping review my examples and making sure I'm not doing anything like, super crazy. So that's it. Thank you very much. I think I have time, so I'm happy to answer some questions if anybody has any. Of course, you can do a lot of really interesting things with unsafe, so let's talk about it online if it's like a really serious thing, but sure. I'm sorry, she's more the microphone, yeah.
Okay, if you're converting between an array to a slice, does that make a full memory copy if you do the square brackets colon, or does it just point the slice at the old array?
I believe it points the slice at the array. Okay. Yeah.
Thanks.
Yep. Don't quote me on that. I'm pretty sure.
Where is the length being stored for the array in memory?
So the length of a Go array is built into the type? You mean for slices or for?
Just for the array. So you're casting from a 16-bit integer to an array. Where is the length of the array being stored?
I think it's stored somewhere in the type information in the Go compiler. I'm not actually sure as far as the internals there, but I know for a slice, it is represented as a field. There's the slice header with the length, the capacity, and a pointer. As far as arrays, I think it's just built into the type system.
Okay.
Yeah. I could be wrong, honestly, but.
Okay.
Cool. Thank you.